Something happened in our solar system that no one was ready for. And what makes this moment even more electrifying is that several experts are already whispering the same unsettling question. What if this event isn't entirely natural? On November 9th, 2025, astronomers Frank Niebling and Michael Buchner captured something so unexpected, so visually staggering, that the scientific community has been scrambling ever since. During a 15-minute observation session, using two separate telescopes aimed at the same target, they photographed the interstellar visitor known as 3I Atlas. What they saw defied every expectation scientists had going into this encounter. In their images appeared enormous jet-like structures erupting from the object, majestic, sharp, and impossibly large. Not one, not two, but three distinct jets extended outward from this mysterious traveler from beyond our star system. Two of these jets were anti-tail structures pointing straight toward the sun, reaching distances that are almost impossible to visualize, nearly 1 million kilometers each. That is roughly 3 times the apparent width of the moon in our sky, stretched into deep space as if drawn with cosmic precision. But the third jet is the one that shattered every prediction. This one didn't point toward the sun, it shot away from it, a narrow, focused beam of material blasting into space for an astonishing 2.85 million kilometers. That's about 7 times the Earth-to-Moon distance. Let that number sink in. We are talking about structures so vast that they make the halos, tails, and jets of typical comets look like specks of dust. 3 orders of magnitude larger than the halo Hubble photographed around Atlas in July. 1,000 times larger. And size is only the first part of the mystery. These jets aren't just large, they behave in ways completely inconsistent with how cometary jets are supposed to behave. To understand why, we need to step back for a moment. When a comet approaches the sun, the heat causes its surface ices to sublimate, turning directly from solid to gas. This creates jets of vapor and dust that can push material outward at modest speeds. In most comets, this outflow moves at around 0.4 kilometers per second, roughly the speed of sound in gas at that distance from the sun. It's gentle, predictable, and powered solely by sunlight, warming cold ices. The process is slow, steady, and limited by the thermal energy available. But 3I Atlas is doing something else entirely. For the jets captured on November 9th to reach the lengths shown in those photographs, the object would need to have been ejecting material relentlessly for months. The long-tail jet, extending millions of kilometers, would require nearly 3 straight months of constant output. The anti-tail jets would require about a month each. That's an almost unimaginable amount of material to sustain such collimated structures. And then comes the part that truly stops scientists in their tracks. Harvard astronomer Avi Loeb examined the data and performed calculations that reveal a staggering requirement for the anti-tail jets to hold their shape while pointing directly into the solar wind. They must have enormous density and internal pressure. The solar wind blasts outward from the sun at 400 kilometers per second, 1,000 times faster than the typical speed of cometary outgassing. Yet these jets appear to be pushing back against that supersonic stream and holding their shape. For that to be possible, Loeb determined that the object would need to be losing mass at a rate of around 50 billion tons every month. 50 billion tons every single month. That number isn't just large, it's comparable to the entire estimated mass of the object itself. Which means that unless Atlas is far larger than we think, the jet activity alone would completely consume it. The only way for an object to survive losing that much material is to be at least 10 kilometers across. But everything prior to November indicated Atlas was considerably smaller. And here's where the next layer of the mystery begins. From July up until late October, 3I Atlas showed almost no activity at all. It was quiet, stable, and behaving like a typical dormant interstellar object. There were no powerful outbursts, no significant acceleration, no high-energy displays. Even as it approached perihelion, its closest point to the Sun, it remained relatively unremarkable. Then came October 29th and 30th. Atlas swung around the Sun, disappearing temporarily behind the solar glare. And the moment it re-emerged, everything had changed. Multiple jets burst into view as if the object had suddenly awakened. It wasn't a gradual warming up or a slow increase in sublimation. It was a dramatic transformation, as if someone flipped a hidden switch. Some astronomers proposed that deep pockets of volatile ices became exposed and heated rapidly at perihelion, igniting a chain reaction that produced the colossal jets. That theory is possible. Comets can misbehave when heated suddenly, but others, including Loeb, have pointed out another possibility, one that is drastically different. What if the observed jets aren't the result of sublimation at all? What if these streams of material are something else? If the jets are natural, the numbers look wrong. The speeds, the mass loss, the density, the duration, everything clashes with comet physics. But if these jets were produced by a propulsion system, the situation changes entirely. Chemical rockets, like the ones we build on Earth, expel exhaust at speeds between 3 and 5 kilometers per second, an order of magnitude faster than sublimation jets. Ion engines reach 10 to 50 kilometers per second. At those speeds, you need drastically less mass to achieve the same thrust. The impossible becomes possible. The unbelievable becomes plausible. Less than 1% of the object's total mass would be needed to sustain all observed jets if the exhaust velocity were high enough. No one is saying Atlas is a spacecraft, but the data is forcing the same provocative question over and over again. Why do the numbers match propulsion better than sublimation? 3I, Atlas, is only the third interstellar object ever confirmed. Oumuamua behaved strangely. Borisov behaved normally. And now Atlas stands in a category of its own, producing structures and behavior that we have never observed before. Its angular separation from the Sun just passed 30 degrees, meaning telescopes on Earth can once again observe it clearly. Over the coming weeks, astronomers will be measuring the composition of these jets, their velocity, their density, and searching for fragments possibly shed during the perihelion upheaval. The story is only beginning. What was photographed on November 9th is just the first chapter, and the next chapters could redefine everything we think we know about interstellar visitors. As scientists race to interpret the sudden eruption of massive jets from 3I Atlas, the object continued to move farther from the Sun, opening a clearer observational window. And with this new visibility came an even more startling revelation. The 3 colossal jets were only the beginning. In the days immediately following perihelion, astronomers began reporting a total of 7 distinct jets shooting outward from the object. 7 separate streams of material, each angled differently, each glowing with its own brightness and structure, forming an intricate web of activity unlike anything previously documented from an interstellar visitor. Multiple jets are not unusual for comets, especially those composed of patchy, heterogeneous surfaces. When sunlight strikes fresh areas, these sites can erupt into localized outgassing plumes. But the scale, the timing, and the configuration of these 7 jets raised immediate suspicion. Normally, when a comet breaks apart under the intense thermal stress of approaching the sun, astronomers can detect clear signs: multiple fragments separating on slightly diverging paths, dust fields spreading outward, measurable surges in brightness as new ice layers become exposed. None of that happened here. The jets were unmistakable, but the core object appeared strangely intact. The question formed quickly: did Atlas partially fracture during perihelion, or is something else responsible for the pattern of activity we're seeing? Comet fragmentation is a well-known phenomenon. Objects composed of loosely packed ice and dust can disintegrate when heated unevenly, splitting into pieces that travel for a short time before fading away. Shoemaker-Levy 9 famously broke apart into more than 20 fragments before plunging into Jupiter in 1994. Other comets have fractured spectacularly near the sun, producing vibrant but short-lived displays. If Atlas experienced something similar, the sudden appearance of multiple jets could be explained by freshly exposed surfaces erupting under intense heat, but this explanation struggles against the sheer longevity of the outflows. The jets from Atlas are not short-lived bursts. They persist for days and, according to calculations, must have been sustained by enormous internal pressure for weeks or even months. Fragmentation events typically produce violent but brief releases of gas and dust, not the massive, coherent structures seen here. The scale is simply too large, the duration too long to fit comfortably within the usual pattern. Which leads to the second possibility, far more controversial but impossible to ignore. If the jets are not passive outgassing, then they may represent active processes that require energy sources, internal mechanisms, or structural features not found in conventional comets. There are natural examples of active geology or cryovolcanism in our solar system. Enceladus sprays water vapor from subsurface oceans through geysers powered by tidal heating. Europa shows signs of similar activity. Even Pluto exhibits nitrogen geysers driven by sunlight. But Atlas is not a moon orbiting a massive planet. It is an interstellar wanderer, a solitary object traveling alone through space. Without tidal forces, the energy needed to drive powerful jets would have to come from within. What could maintain that level of internal pressure? What could synchronize the release of 7 jets at once? This is the point where theorists begin to consider options that stretch beyond typical explanations. If an interstellar craft needed to conduct maneuvers, there would be no better moment than perihelion, when its velocity is highest and when small adjustments have maximum impact on trajectory. A spacecraft would also conserve its fuel during interstellar flight and only activate powerful systems when necessary. The sudden onset of Atlas's jets, precisely at the moment it rounded the sun, fits that timing almost impeccably. But no direct evidence of artificial technology exists in the images. No symmetrical structures, no metallic surfaces, no engineered geometry, just jets, huge, powerful, persistent. That alone is enough to keep both camps debating fiercely. As observations continued to pour in, the scientific world shifted its attention toward identifying the composition of the jets. Natural sublimation produces signature molecules: water vapor, carbon monoxide, carbon dioxide, various organic compounds. Spectroscopic analysis of Atlas in the coming weeks would determine whether those expected signatures are present or whether the jets are composed of materials that do not match typical cometary chemistry. If the jets turn out to be unusually pure, unusually mixed, or entirely unexpected, the natural interpretation becomes harder to defend. Meanwhile, researchers began tracking the trajectory of Atlas with extreme precision. This is where some of the most crucial information will emerge. When a comet ejects material in one direction, it experiences a small push in the opposite direction. That push, if large enough, can be detected as a deviation from a normal gravitational path. Non-gravitational acceleration is common in comets, but the acceleration matches the direction and strength of the observed jets. The key question now is whether Atlas's motion aligns with the jets we see, or whether the trajectory is being altered in ways that do not correspond to natural outgassing at all. If the object continues to change direction without any clear link to the jets, the conversation will shift dramatically. Another major question: did Atlas break apart or not? If fragmentation occurred, multiple nuclei should now be detectable. Each fragment would drift slowly away on its own trajectory, creating a spread pattern that sensitive telescopes could pick up. Yet early observations show something surprising. The object appears intact. For a body experiencing such violent activity, such intense heating, such dramatic mass loss, this level of structural integrity is unexpected. Natural comets rarely survive these conditions without cracking or shattering. If Atlas has a robust structure, one capable of resisting the immense stresses of perihelion and sustained mass loss, that is itself an anomaly. Natural comets are fragile, brittle relics from the early solar system. Atlas, by contrast, seems unusually resilient. As days pass, astronomers continue to monitor the intensity of the jets. Natural sublimation declines gradually as ices evaporate and as the object moves farther from the sunday, but if the jets maintain strength longer than expected, or worse, turn off sharply instead of fading, that will be another signal pointing away from standard comet behavior. And this brings us to a frustrating turn in the story. While telescopes on Earth are gathering new data every night, the best vantage point, the Mars Reconnaissance Orbiter's HiRISE camera, captured detailed images of Atlas just before perihelion, when the object was still quiet. Those images were taken at a staggering 30 kilometers per pixel, enough to reveal the outline of the nucleus and possibly early jet structures. But the images have not been released. A government shutdown in the United States paralyzed NASA operations, leaving critical scientific data locked away for more than a month. The timing could not be worse. Those pre-outburst images may hold the key to understanding how Atlas transitioned from a dormant traveler to a hyperactive phenomenon. Without them, scientists are working with incomplete clues. Earth-based observatories resumed full tracking of Atlas on November 11th, collecting spectra, brightness variation, measurements, and structural data. But the missing HiRISE images create a gap, one that grows more significant as new jets form and evolve. The longer the delay, the harder it becomes to compare before and after observations. Researchers, space enthusiasts, and even members of Congress are publicly asking a simple question: where are the images? And more importantly, why are they not being shared? As the world waits, the story of Atlas grows more complex and more fascinating. Every night brings new measurements, new surprises, new contradictions. Each data point pushes us closer to an answer, yet further into a mystery. Whether natural or not, Atlas is rewriting our understanding of interstellar visitors. And the next few weeks will determine which explanation survives. The most revealing chapter of this unfolding mystery may be the one we have just entered. With 3I, Atlas now fully observable from Earth, astronomers around the world are accelerating their efforts to collect every piece of data possible before the object slips away into the darkness of deep space. And the closer researchers look, the more improbable the object appears to be. As new calculations emerged, one particular detail began shifting the tone of scientific discussions: the sheer mass of Atlas. Based on the jet activity we've witnessed, the amount of material required to sustain such enormous structures, and the duration over which they persisted, the minimum mass of the object must be at least 33 billion tons. If the nucleus survived perihelion largely intact, its diameter may be 10 kilometers or more. That places Atlas in a completely different league from Oumuamua, the first interstellar object discovered in 2017, which weighed in at perhaps 30 million tons, a difference of 1,000,000 to 1. That ratio alone challenges everything astronomers expected about interstellar object populations. If objects enter our solar system randomly from the galaxy, small ones should dominate the catalog. The chance of the third detected interstellar visitor being 1,000,000 times more massive than the first is vanishingly small. Calculations suggest the odds sit somewhere around 1 in 1,000 or far worse, depending on assumptions. And this isn't the only improbability weighing down the natural interpretation. Atlas arrived on a retrograde orbit, traveling against the direction planets move around the Sunday. That part is unsurprising. Interstellar objects can approach from any direction and at any inclination. But what is remarkable and statistically alarming is that Atlas entered the solar system on a trajectory aligned within barely 5 degrees of the ecliptic plane, the flat disk where the planets orbit. Out of all possible angles spanning the entire celestial sphere, the object just happened to arrive almost perfectly aligned with the region of space most densely populated with planets, moons, and human instruments. The probability for such alignment is about 0.2%. Taken together with the mass-related improbability, the combined odds plummet to around 1 in 100 million. That doesn't mean Atlas is artificial, but it does demand deeper investigation. Science requires reevaluating assumptions when probability stacks itself so aggressively against the simplest explanation. One possibility is that our understanding of interstellar object formation is wrong. Perhaps the galaxy is filled with far more massive drifting bodies than astronomers previously believed. Maybe giant fragments from distant planetary systems get ejected far more often than models predict. If that's true, then Atlas is simply the first of many such visitors we will detect as our observing capabilities improve. The upcoming Vera C. Rubin Observatory is expected to discover dozens or even hundreds of interstellar objects every year. If most of them resemble typical comets or asteroids, then Atlas will stand out even more dramatically in contrast. But there is another path the data could follow. If additional interstellar objects arrive with similarly unusual properties, unexpected masses, peculiar orbits, unexplainable accelerations, then patterns may begin to emerge. Patterns that point toward intentional trajectories rather than chance encounters. Patterns that resemble behavior rather than randomness. Oumuamua already pushed scientists into uncomfortable territory. It accelerated without outgassing. It produced no dust, no gas, no tail. It reflected sunlight in ways that hinted at an unusually flat or elongated shape. Some researchers proposed exotic natural explanations. Others suggested it might be the remnant of technological debris, like a thin solar sail drifting through the galaxy. Atlas, with its massive jets and puzzling behavior, is now forcing many of the same questions back onto the table. If Atlas is natural, then it is teaching us that interstellar space harbors objects far more diverse, complex, and active than anything we have imagined. If it is not natural, even partially, then the implications are far more profound. Humanity would be witnessing the first confirmed technological artifact from another civilization. It would mean we are not alone. It would mean interstellar travel is possible, not just in theory, but in practice. And it would mean civilizations far older than ours may have explored the galaxy long before humans invented writing. But evidence is what matters now, and the next several weeks will determine which direction the evidence leans. Spectroscopy will reveal the chemical fingerprint of Atlas's jets. If the jets contain normal cometary materials, water vapor, carbon monoxide, hydrocarbons, that would support a natural interpretation, though it would not rule out internal processes that differ from traditional comets. If the jets contain unexpected ratios, rare elements, or compound structures inconsistent with known comet chemistry, the conversation changes immediately. Velocity measurements will determine whether the jet speeds fit the thermal model of sublimation or point toward a different energy source entirely. If the jets exceed 1 kilometer per second, speculation will intensify. If they reach several kilometers per second, many natural models collapse. Trajectory analysis will reveal whether Atlas is being pushed by its own jets or by something else. Even tiny deviations from a pure gravitational path can betray the presence of directed thrust or asymmetric mass release. If the object's path is being corrected, steered, or stabilized, it will show up in weeks, not years. And then there is the missing high-rise data. The Mars Reconnaissance Orbiter captured the only side-view imagery of Atlas during its inbound trajectory, taken at the closest relative approach to any spacecraft. Those pictures may hold the most important clues yet, details about the nucleus, its shape, its surface, its structural complexity before the jets erupted. Every day of delay increases the scientific cost. That data represents a frozen snapshot of Atlas before its transformation. Without it, researchers are studying only half the story. On December 19th, Atlas will reach its closest distance to Earth, 269 million kilometers. Far, but near enough for powerful telescopes to capture images more detailed than anything available now. This is the moment astronomers are preparing for. Observation schedules are already full. Instruments are calibrated. Teams are coordinating globally, sharing data, comparing findings, and working on theoretical models that stretch the imagination. The next month is a race against time. After January, Atlas will drift farther away, growing dimmer. Its jets may weaken or vanish. Its structure may stabilize or fracture. The window to learn from this visitor will narrow rapidly. And once it exits the solar system, humanity may never see it again. This is why the scientific community is urging the world to pay attention. Events like this do not unfold often. In the entire history of astronomy, humanity has witnessed only 3 confirmed interstellar objects passing through our solar system. And 2 of them, Oumuamua and Atlas, have behaved in ways that defy easy categorization. This is not just a rare moment. It is a historic one. Whether Atlas turns out to be a colossal natural comet, a fragment of a shattered alien world, or something that carries traces of technology, its passage is reshaping our understanding of the universe. It challenges our assumptions. It expands our sense of possibility. It forces us to rethink where we stand in the cosmic landscape. And most importantly, it reminds us that discovery is not a finished chapter in human history. It is happening right now. The universe still holds mysteries vast enough to humble us and close enough for us to see. As the world waits for the next data release, telescopes continue to track the object through the night sky. Every spectrum, every pixel, every shift in brightness adds another clue to the puzzle. And somewhere out there, millions of kilometers away, Atlas continues its silent journey, a stranger from another star system, carrying secrets we are only beginning to uncover. The final answer may take weeks, months, or years. But one truth is already clear. Whatever Atlas is, its appearance marks one of the most extraordinary scientific moments of our lifetime. And the story is far from over.